Hello dear colleagues and welcome to Civil Curious channel. In this video we are going to continue our tutorial about concrete columns. In the last session we talked about the general thing like uh, the pure axial load endurable by column and what is the nominal strength in tensile and compression for columns, and we solved three problems about concrete column, and I hope you all have that enough view and enough comprehension of concrete column. In this session, we're going to continue our lesson. Let's get started. First of all, in this session, we're going to introduce the center of plasticity in concrete columns. Let me write that. So, center of plasticity of concrete column, or we call it XP. What is center of plasticity? Center of plasticity is a point that if all of loads act in this point, our section is in equilibrium. Both of tensile and compressive loads are in equilibrium. Let me show that for you in the shape. You see, I want to draw a concrete column. I apologize again for such a drawing. As I said you, these are our AS, A prime S, and these are our AS. A, okay, this is A prime S and this is AS, and this is the distance between reinforcement, okay, and I'm gonna name the bits of our column as B, okay, and the clear cover for compressive rebars is D prime. Let me name all of uh, uh, corners in column. I'm gonna name it A. This is C. This is B, and this is D. And the center of plasticity is somewhere near here, and P0 is acting in this point, and the distance from center of plasticity to other side of concrete column is XP, as I said above. How can we calculate this center of plasticity? For calculating this, we have to make a moment equation about side AB. It's my method. You can, for example, make that equation, moment equation about side CD. But in this problem, I'm going to solve this equation about side AB. Let's get started. I'm going to write that if let's make a moment equation about side AB, this side. We have here P0 times XP is equal to the load, the moment of concrete about side AB. I'm gonna write that uh, uh, here, let's here. Load of, no, I'm gonna write it like this. The load of concrete, that I'm gonna name that FC. Let me name that M, because we are talking about moment in this problem. MC, which is moment of concrete uh, about side AB, plus the moment of all of the states, like tensile reinforcement and compressive reinforcement, which is M of all of steel, which is A prime S plus AS, times uh, no, that's it. The moment of all of reinforcement about side AB. Okay, this is the equilibrium of moment for calculating the center of plasticity in concrete columns. And how can we write that in mass relations? In this equation, we can write this equation like this. We have xp. Let me change my marker. No, this mark is okay. We have xp, which is equal to, in the last session I told you that the load, the force of concrete is 0.85 F prime C. If you forgot that, you can return to that video, times the gross area minus the area of all of the steels. This is the force of concrete. If we multiply this parameter times H divided by 2, this all of these sentence will be the will be the moment of concrete. Okay, I'm gonna, and we add this parameter to moment of all of the steels. We have A prime S times D prime here. A prime S times D prime plus AS times D. This is D, times the yield stress of steels. All of them are the moment about side AB. Okay, and we have to divide all of these parameters to these parameters. 0.85 F prime C times AG minus A steel plus A steel times yield stress of reinforcement. This is the relation of center of plasticity in concrete columns. Okay, I forgot to show the height of columns. This is h, the total height of column. Okay, and now let me show you what is happening in stress of concrete and rebars. Sorry, concrete columns. Apologize. Okay, we know that in the ultimate state, all of reinforcement has achieved to their yield stress. We have yield stress of tensile reinforcement, and we have here yield stress of compressive reinforcement that we call it F prime y. Or all of both of F by and F prime by are equal. Okay, and we suppose that concrete has uniform stress. You know, in the last session we discussed about this. And the value of this stress is 0.85% of F prime C. This is the situation of tensions in concrete columns in the ultimate state. And we have this enough view of and enough comprehension of center of plasticity in concrete columns. And if you all agree, I want to solve some problem for you to understand that better. I think one problem would be okay, because I'm not gonna spend more time for that because our topics are more in this session. Okay, and we're gonna discuss about other things for concrete columns. And now I want to solve a question for you. Suppose that we have a concrete column here. Let me draw this section, and like always I apologize for my drawing. Okay, we have here AS1, and we have here AS2, and the dimensions of our column in this side is 600 millimeters. Our unit is millimeter, and in this side we have, sorry, and in this side we have our dimension (400 millimeters). Okay, and the distance between the center of reinforcement to this side of concrete is 60 millimeter, and the distance between the center of uh, reinforcement to this side of column is 62. Okay, and we have the applying force or action, our demand, as PU. I told you in the last session. Here we call it PU, which is applying in this side of concrete. Okay, and we have our concrete is 330. Our strength is 30 megapascal, and our reinforcement are is 400. Okay, and what the question want us is to calculate the ultimate moment applying in this column. What is what we are going to solve is mu applying in this column. We have the pu applying in this column, and what we're going to calculate is the mu. Okay, according to we have want to calculate mu according to pu. Okay, and what the question uh, give us is AS1 is equal to 2500 millimeter square millimeter, and AS2 is 1400 square millimeter. Okay, let's solve this problem. We all know that if we calculate the moment of PU about the center of plasticity, which we supposed to be something like something around here. We suppose the center of plasticity near here. Okay, and this is our ultimate force P. We name this distance as xp. Okay, and we know that if we our mu, or the answer of question mu, is equal to pu times the center of plasticity. Okay, this is our answer. Okay, we want to make this equation. Okay, and how to calculate the center of plasticity. Let me review that for you. The center of plasticity is going to be calculated with this method. xp is equal to 0.85% of f prime c times the gross area minus the area of the steels time h divided by 2, the half of our dimension, plus AS1 times D1. You know, this is D1 I told you before, plus AS2 times D2 times the yield stress of steels, you know, divided by 0.85% of F prime C times the gross area minus the area of steels, plus the area of steels times the yield stress of steel. Told you, okay. What is D1 and D2? You have to know that uh, we're gonna make this moment equation, about the side of this side of concrete column, okay, and that would be the D1, this distance, and that would be the D2, okay. I'm gonna continue. XP is equal to 0.85 times 30 as data of problem times the gross area is 600 times 400, okay, minus the area of steel, which is given by our problem, 2,500 plus 1,400, okay, that's it, times the half of our h. This is h, the total height of our section, okay, which is 600 divided by 2, okay, plus AS1 is 2,500 times D1 is 600 minus 60, which will be 540, plus 1,400 times D2 is 60, okay, times 400, which is the yield stress of concrete of reinforcements. All of these divided by these were the moment, and we're gonna divide these moment to force of concrete and steels. 0.85 times 30 times 600 times 400 minus 2050 plus 1,400 plus 2,500 plus 1,400, okay, times 400, okay. This is our XP. I've calculated that, and our answer is 313.9 millimeters, okay. And as I said to you, our answer is mu, which is equal to pu times e, or e is xp, which is equal to our mu is 313.9 times pu, and I'm gonna transfer that to meter, kilonewton and meter. So because of that, I'm going to multiply that to 10 to the power of minus 3, and our answer will be equal to mu is equal to 0.31 of pu in unit of kilonewton meters. That is our answer, everybody. I hope that this problem was enjoying for you. I want you to show you a problem that is solved about center of plasticity. I want to give that view for you, to have better comprehension and understanding of about central plasticity. I'm gonna move this topic, and I want to open another topic in concrete columns. Everybody, let's get started. Now I want to discuss about this issue that uh, is I want to tell you what is happening when our column is subjected to both moment and axial force. Suppose that this is our concrete column. This is our concrete column, and this column is subjected to one a axial force, which I name it P, and another moment that I name it M. You know, and there is not here our pure axial load that we name it P0. We don't have those equation here. Okay, and what is happening in this section of concrete column is like this here. Let me draw our section for you. This is our concrete section, which has 3 reinforcement in this side and 3 reinforcement in this side. Okay, and we have here this side. I'm gonna name it B, the dimension of this side, and the distance between. Let me change my marker. I'm going to name all of these corners. We name here A, and this is B, and this corner C, and this corner D. Okay, and the distance between the center of this reinforcement to the side of BC, is D prime. Okay, and the distance between this side of reinforcement, center of reinforcement, to this side as D. Okay, and the let me name that AS, and these are A prime S, which are compressive reinforcements. Okay, and our axial force P is applying in this point. Okay, is applying in this point, and which I'm gonna name it P, and our moment is applying from side AD to BC, and this, and I want to show that like this. This is the how we show moment in civil engineering, and this is M. Okay, this is P. This is how we show. Uh, One side of our section is in tensile, and one side of our section is in compression. Okay, and what would be the shape of a strain of both steel and concrete in our column? This is the shape of stress, strain in our column. Okay, we have the strain of crushing concrete here in the forest side or side of BC, and we have here the strain of compressive reinforcement here. You know, let me write that the strain of compressive reinforcements, and we have here the strain of tensile reinforcements. Okay, and here we have the distance of plastic center of plasticity. Okay, this is how this is what this is the strain in our column, and that is our stress in our concrete column. Okay, for better understanding of this problem, let me show you the stress in our column, everybody. Let me draw that again. Okay, and I'm going to tell you that this area is compressive area, you know. Okay, and this is our side B. Okay, and this is our dimension of concrete area, which in ACI code or other codes in civil engineering we named it as alpha 1, which is equal to beta 1 times x. Okay, and the area of uh, sorry. And the area of compression is equal to beta 1 times x times b. Okay, and this is the area of compression that which is named as AC. Okay, and I want to show you another picture of a stress. Let me make it simplify and drawing. I'm going to show that it's just a line. This is the tension of stress, the tension of tensile reinforcement, and here we have area of compression area, and we have the tension of concrete, and as I said this is alpha, which is equal to beta 1 times x, or beta 1 x, and the value of tension is alpha 1 f prime c. Okay, we have the stress of steels and we have the stress of compressive reinforcement, which is named by f prime s. Okay, this is the this is the strain distribution, and this is a stress distribution. Okay, I wanted to show you what is happening when a concrete column is subjected to both axial load and moment. You know, this is how our columns behave here. And now I'm going to let me make correct this parameter. We call this parameter A, not alpha 1. Sorry. This area is A, and we have here A. And how our nominal strength of column would be calculated in this circumstance? Okay, I'm going to just write the whole equation, and I'm not going to make it too far for you. Just want you to know this equation. We have here our nominal strength P n. We have our nominal P, which is equal to alpha 1 times f prime c times the area of block tension. Okay, area of compressive block, which is A times B. I mean this area that I highlight that for you, plus the stress of steels times the area of compressive steels, minus, because the direction of movement is different from tensile stress, tensile reinforcement, and compressive reinforcement. Okay, minus the stress of tensile reinforcements times the area of tensile steels. Okay, I want to ask you a question. Uh, why do you know that why I do not write the yield stress of steels? As you can see, I write F prime S and Fs. I didn't write F prime Y or Fy. The answer is we don't know if our steels achieve their yield stress or not in this circumstance. Okay, we should be so careful about that. Let me make a circle on this equation. And I want you to know how can we calculate the nominal moment, nominal strength, nominal moment strength, of column in this circumstance. How can we calculate that? You know that? If in this section the center of plasticity would be determined, if we all know that we can calculate the nominal strength of moment for concrete column, and I just want to write for you the nominal moment strength for you. Let's get started. I address that. We know the center of plasticity in this circumstance. Let me write that. Our XP is determined. XP is determined. Okay, don't forget that. Let's get started. Our nominal moment strength is equal to alpha 1 times F prime C times A times B, I told you, times the center of plasticity minus A divided by 2. Because for example, suppose that here is our center of plasticity and here the half of our block tension, and that would be the distance for calculating of moment of concrete. Okay, which is this area minus this area. Okay, plus F prime S times A prime S, times the center of plasticity minus D prime. I will explain you. Plus the stress of steels times AS, area of steels, times D minus center of plasticity. Okay, let me change my marker to explain you. This parameter is the concrete force. This area is concrete force. Okay, and this area is distance for calculating of moment of concrete. Okay, and this parameter is steel force and this parameter is steel force 2, and both of this parameter and this parameter are the distance for calculating moment of steel about side BC. Okay, if you work uh, if you work alone you can't solve it. Okay, if you look at this equation and you can't understand, don't be worried about that. You can calculate that uh, uh, alone at home and be such as it be peaceful at home. Okay, uh, that is the moment and axial force the applying and subject applying our in our concrete column, and our concrete column is subjected to this force, and that was our calculation. I know we spent so much time on that, and but that was so important for us in civil engineering. And now I want to show you the curve of concrete column which both moment and axial force occurs on it. Okay, let me show you. And this I'm drawing is the renowned uh, curve for concrete columns. Which are subjected to sorry both axial force and flexural moment. Okay, the vertical side would be Pn and the horizontal side would be Mn. Okay, and our curve has such a this shape. Okay, this is the shape of our curve. Okay, and in this point we have, let me show that. In this point, let me highlight this point. Okay, okay, remember this highlight line. Okay, in point A, let me name these points. This is point A, and this is point B, and this is point C. Okay, this point is P0, and in MC we have pure moment or M0, and in the point B we have MNB and PNB. Okay, let me write that. Here we have Mn, and here we have Pn. Okay, and Now let me explain for you what is this point. Okay, uh, in the point p0, in the point p0, the curve tells us there is no flexural moment, and our concrete column is subjected to pure axial force. Let me write that for you. There is not a flexural moment, and we have pure axial force. Okay, and the point C, here we have point A, and the point C we have M0, which tell us uh, there is no axial force, and we have pure flexural moment. Okay, and in point C, sorry, and in point B, there is both axial force and flexural moment. You know, we have that. And the thing that we can concentrate on it, we have in this point C, which we have pure moment. Our column acts like a beam, You know, you have to remember that and know that. And in the point A, we have pure axial load, and there is not any moment. We have to know that all of load, which is P0, is acting on center of plasticity. This is a really important point. One of the important things we have to know about concrete column is that if our load of concrete column be inside of this curve, be inside of this curve, our concrete column is safe. And for loading that is out of this curve, our concrete column is condemned to death, will be crushed, our concrete. Okay, this is another really important point that you should know that. Okay, and another thing that we have to know for concrete columns is that for concrete columns which are subjected to interaction of both axial force and flexural moment, this curve is a bit hard for us for analyzing. And engineering, for simplifying that, make it a two line, okay, like this. And we have to know that this line would be approximate, and this is not and not exact like a curve. Okay, this is our simplified and approximate line. This is better for analyzing of concrete columns because we can write the equation of this line and we can calculate our P and N. But for that curved line, analyzing of concrete is a bit hard, you know. Now I want to close this topic. This topic is the wall, believe it or not. But we cannot spend too much time for that. I want to open another issue for concrete column. Okay. At the rest of our session, I want to tell you some about reinforcing of concrete columns. Okay. Uh, you know, I want to know. We want to know that how can we set steel in reinforcement? For example, if we are allowed to set, for example, 30, 40 of steels in concrete columns, no. The basic codes, concrete codes, have limits for that and don't allow us to set to set what steel we wanted, you know, and this is not, this is controlled by codes. We have the by the this is controlled by codes by this equation. We have the percentage of steel in concrete column. The relation is here. The percentage of steel in concrete column is equal to the area of a steel divided by the gross section of concrete column. This is the percentage. And the value of rho is controlled by code and is equal to, sorry, would be at least would be at least 0.01. Okay, or we can write it like this: the area of steel would be greater than 0.1 percentage of gross section. This is one of restriction of concrete codes that don't that force us to have or set enough steels in concrete column. And another restriction is for the maximum number or maximum area of steels in concrete column. We have rho as area of steel divided by area of gross section, and the area of steel should be less than 0.08 percentage of gross section, and this is great. The concrete code force us not to set every steel we wanted in concrete columns. So we have learned that the area of steel in concrete column has normal value, you know, that concrete codes force us to obey them. Okay, we can write here the percentage of steel should be at least 0.01 and maximum 0.08. So the area of steel should be greater than 0.01 area of cross section and the maximum 0.08% of cross section. That's it. In this session, everybody, we talk about the center of plasticity of concrete columns, and in continue, we discuss about the curve line, uh, which shows the interaction between axial force and flexural moment, and I showed you what will happen in our section when our concrete column is subjected to both axial force and flexural moment. And in the end, we discussed about the percentage of steel in a concrete column. Okay, I hope you all enjoy my video about concrete column in these two sessions. I know these were not perfect, but I hope that to make a good video for you in calculating concrete columns, and I hope that you all enjoy it, everybody. Uh, if you ask any question, I will do your service, and I thank you all, everybody. Thank you very much.